U substitution allows you to evaluate more complicated integrals. Up until now, you've mostly been dealing with the integral, finding the antiderivative of polynomials or something like that, but that is pretty limited in scope, so we'd like to be able to handle more complicated things. For example, let's suppose we want to find the indefinite integral of this function. So we have 2x times the square root of x squared minus 7. So yeah, this is a lot more complicated than just, for example, the integral of x cubed, and we have to know how to deal with this. And the right way to do this is to use something that's called U substitution. It's a really general technique that's applicable for a lot of different integrals, and I think the best way to really learn it is just to do a bunch of practice problems and just see, just get familiar with it. So here's how it generally goes. The main point is that you must be able to identify one part of the integral as the derivative of another part. So when I'm looking at this function right here, 2x times the square root of x squared minus 7, alright, so I get to thinking, and I look at this part here, this x squared minus 7, and I say, alright, well, the derivative of x squared minus 7 is equal to 2x. And this right here, this 2x, is exactly what we have out in front. So this is why U substitution is going to be useful in this case. And this is always the general method. You find something, one part of your integral is going to be the derivative of another part. So here's what we do. We make what's called a U substitution. Now why do they call it a U substitution and not a Y or X substitution? No idea. It's just convention. So, that's just what people do. Anyway, so we make the substitution. U is equal to x squared minus 7. So then if we looked at the what's called the differential, basically just taking the derivative of each side, we would find du is equal to 2x dx, and that's it, right? Because the derivative of a constant is 0. And then we notice that this part, 2x dx, is exactly what appears here, 2x and dx. So we can substitute du in for 2x dx. And then this part, x squared minus 7, is equal to u. So we find that this is equal to the integral of, alright, so square root of x squared minus 7 becomes the square root of u, and then 2x dx becomes du. So this is a lot easier, right? This is just a polynomial function, right? It's u raised to a power, u to the 1/2, and we know how to evaluate that antiderivative. Right, so this is just going to be equal to u to the 3/2, and then we divide by 3/2, which is the same as putting a 2/3 out in front, right? So that's just the normal way you evaluate polynomial integrals. And then now we don't want our answer in terms of u, we prefer it to be in terms of x, because that's what we started with. So this is equal to 2/3, and then u is x squared minus 7, all to the 3/2. And that's it. So we were able to evaluate the integral. At this point, I wouldn't be surprised if you were still a little confused, because it's a little, difficult topic, but I hope you can see how this would be a really powerful tool, right? Because there are, there's going to be a lot of different kinds of functions that are going to fit this bill, and now we're going to be able to integrate them. So like I said, the best way to understand this is just to look at a bunch of different examples. So I'm going to throw another one up here. This time we have sine cubed of theta times cosine theta d theta, the integral. Right, so this time I'm using the variable theta instead of x, but it's really no different, right? Within an integral, an indefinite integral, you never have to worry about, the integration variable. Don't let that confuse you. Okay, so this fits the bill, basically, because we have to identify one part of the integrand as a derivative of another, roughly. Like there's a little bit of an art to this, but you understand. Well, we know just from maybe your first semester that the derivative of sine of theta is equal to cosine theta. So that's a good place to start. So if we take u, here's our u substitution, equals the sine of theta, then we get that du is equal to cosine theta d theta. Now maybe it's still a little weird writing these differentials for some of you. You know, I'm not going to rigorously prove why this is all okay to do, but you know, I think it makes sense for the most part. If you're, you know, maybe a little confused, you can always bring this over to the other side and you find that du d theta is equal to cosine theta, which is exactly what we knew, right? So d theta of u, which is sine theta, is cosine theta. So we write it like this. And now we see this part right here, this cosine theta d theta, is exactly what we have here. I'll do examples later where it's not exactly the same, but you know, let's start off with something simple. I think that's the best way to do it. So we put, yeah, now we're ready to make our substitution. So this is equal, well, sine of theta is u. So we have sine cubed of theta, so that's the integral of u cubed. And then cosine theta d theta is equal to du. Not too bad. All right, here we go, another polynomial integral. So this is equal to, well, we raise the power 1, so 3 becomes 4. And then we divide by the exponent, so that's 1/4, u to the 4th. And of course, we don't want our answer in terms of u, we want it in terms of theta. So u was equal to sine of theta. So this is 1/4 sine to the 4th of theta. If we're being really rigorous, there should also be a plus c here, right? Because this is just the antiderivative, and that's only defined up to a constant. You know, this is an indefinite integral. There aren't bounds here. You know, it's not like it's from a to b or something. So we have to add the c, and yeah, that should also be present for the first example. In the next video, I'll talk about integrals that have bounds too, right? So definite integrals, and how we can approach that more easily with u substitution. And as always, if you have any questions, please post them in the comments section, and I'll try to answer them. And if you like the video, you know, why don't you subscribe to our YouTube channel and check out the website. All right, thanks guys.